Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 59 of, sorry not 59, 50 of electrical machines subject. So today we will discuss about the equivalent circuit of a non-salient pole cylindrical pole rotor. What is the equivalent circuit? And from there we will do the numerical analysis, right? What is the phasor? We will draw the phasors and we will understand the angles. Also we will do few questions on whatever we have learned today. Okay, so the equivalent circuit per phase equivalent, right? So per phase equivalent will be, in the previous lecture we had, or like I had already given you a brief how the circuits and all those things will look, right? So basically per phase equivalent I will have a sinusoidal induced EMF that will be known as E resultant EMF ER, right? So whose, like I will write the phase angle later. So again that will deliver through the armature power to the load. So load is here. Load is here. Okay, now now the important point, is that what you have to understand is that if the armature is supplying delivery power to the load, so it has to supply through a wire, right? And that is known as the armature winding. So armature winding will have its own resistance known as armature resistance. That is true. Again, one more kind of drop there will be, that is known as the, like the winding is like a inductive, right? Inductive winding, so it will have a leakage reactance, right? Air gap flux will have a leakage reactance. We have already discussed what is leakage reactance, so again I'm not explaining you and wasting your time. So it will have a leakage reactance, so like this it will deliver the power. Now one more effect we saw, right? What was that? That was the effect of armature reaction. Armature reaction, right? Depending on the armature reaction, it can actually change the resultant air gap mmf, and if the resultant air gap mmf is changed, then the induced emf also will be kind of changed. Basically the output voltage, I will get a different output voltage, right? The resultant air gap mmf. So what will happen, I will have a coil, but it can be capacitive as well depending on what kind of load it is connected, right? This is known as the armature reactance, that is variable actually depending on the load. Okay, that will keep on changing, right? So this is the point of my field mmf, okay, ef, or also known as e only. Okay, and this we write e only, and this is the point where the, if you remember, this was the point where I used to get the resultant mmf, right? After the drop of the armature reactance has been accounted for. Okay, and this is the terminal voltage that I will get at the output. So what voltage the load will see? The load will see this Vt. Okay, this will be the terminal voltage. Load will see the Vt. Okay, this is the terminal voltage Vt. Load will see the Vt only. Load will see this terminal voltage Vt. Okay, and yeah, that's it basically. I hope you have understood this basic point. So we actually make our terminal voltage to be the reference. Okay, we keep our terminal voltage to be the reference because that is the easiest way with which I can derive everything. So the load current is known as Ia, so it can have an angle of theta. Okay, so ER angle, I don't care about this ER angle. This is just internal to the machine. I don't care about this. Okay, so ER is known as the air gap voltage or voltage behind the leakage impedance, right? All this have been defined. So this is also known as the air gap voltage. Okay, and E is known as the like excitation voltage, right? EF or E. So E excitation voltage. Okay. Now the angle of this excitation voltage with respect to Vt is known as the delta, which is also known as the power angle in case of generator, or torque angle in case of motor, right? Why is it called torque angle or power angle? Because in this delta, the information about the active power is hidden. Okay, the information about the active power is hidden. That will prove it to you when we will study the power flow. Just for a second, trust me on this, that this delta actually has a hidden information regarding the power flow. Okay, active power flow. Trust me, I will explain this when we will discuss about power flow in synchronous motors, synchronous machines, generator and motor. Okay, just trust me for a second. Okay, so these are all the values basically: Vt angle 0, I angle theta, E angle delta. There are other angles as well that I will discuss. Okay, so Vt is known as the terminal voltage. Vt is known as the terminal voltage that the load will absorb. Okay, terminal voltage that the load will absorb. Now let's discuss what will be the what is the this induced EMF E equals to with respect to the phases. So induced EMF E will be equals to, first of all, Vt, just simple KVL, right? Vt plus Ia into Ra plus Ia into JXL plus Ia into JXAR. Okay, and remember this is a variable kind of thing, so this will vary basically. This will not be always plus, right? This can be negative as well, this can be capacitive as well, this can be inductive depending on the load. Remember, right? This we have discussed. So ultimately my E will be equals to Vt plus Ia into Zs, where Zs is actually known as the synchronous impedance. Synchronous impedance, basically impedance of the synchronous machine, synchronous impedance. Now this ZS, remember, is variable, right? Depends on the type of the load that is connected, whether it is leading, lagging or something, right? Okay, depends on the type of the load. Okay, I hope you have understood this basic thing. So like this Zs is actually equals to Ra plus Jxs, where your xs, right, I will write here only, your xs is actually equals to combination of the reactance plus the armature reaction. Now again this is variable, so I have written here with a what is this sign, wave sign. I don't also remember what this sign is called. So this can be plus or minus, right? Anything depending on the armature reaction, whether it is magnetizing or demagnetizing. Okay, so these are the key points whatever I have discussed written over here. So EF is known as the excitation voltage. This is the voltage induced in the stator armature when the rotor is excited and spinning at synchronous speed when no load is connected. It is governed by the field current and the machine's construction. ER is the resultant EMF, air gap voltage or voltage behind the leakage impedance. It is the internal voltage generated after accounting for armature reaction. So due to armature reaction, either the overall flux will increase or decrease, right? So taking into account, that will be the resultant EMF here. That is also known as the internal, that is also known as the internal voltage. What is it? What is internal voltage generated? Okay, we are not interested in this because we cannot actually measure it properly. We can never measure it. Okay, so it serves as an intermediate quantity between the field excitation to the voltage. Okay, this is a variable quantity. Okay, so we can convert this whole thing into a single impedance known as the ZS, known as the synchronous impedance. Okay, and XAR, I have already told you that the armature reactance, it models the demagnetizing or cross magnetizing or magnetizing. With all these three things, it can. Okay, of armature current on the main field flux. Okay, R is the armature resistance, XL is the leakage reactance. So ZL is known as the leakage impedance, which is combination of RA and XL, and XS is known as the synchronous reactance, which is a combination of armature reactance and the leakage reactance, and ZS we have already discussed, right? So these things already we have discussed. Now let's quickly draw the phasor diagram. Okay, let me draw the phasor diagram. So if I want to draw the phasor diagram, how will I draw it basically? So let me actually, yeah, let me draw it for a lagging power factor basically. So let's start with synchronous generator with a lagging power factor load. So do you remember what used to happen with a lagging power factor load? What used to happen to the synchronous reactance? Do you remember it? So I will just give you a quick overview. So here was my flux phi f, here was my mmf ff, right? And my induced EMF used to lag the flux by 90 degrees. This was my EF, right? In case of generator. Now, as the load is lagging, right, or lagging power factor, meaning from these two terminals, right? I will copy the circuit. From these 2 points, right, as the load is lagging from these 2 points, as the load is lagging from these 2 points, what I will say is, like, basically EF, the current IA will lag the voltage here, but it will not be totally like purely inductive, right? Previously we discussed for a purely inductive. Now let's say it is not purely inductive. If it is not purely inductive, the current IA will be somewhere here, it will lag. So this will have two components. One will be cross magnetizing component. So in the previous lecture we discussed about purely lagging load, right? One will be cross magnetizing, one will be demagnetizing, because this will produce a flux in the opposite direction. This will produce a flux in the vertical direction. So basically this will demagnetize this flux. So overall the flux will get reduced. So overall the effect will be cross magnetizing plus demagnetizing. Overall the effect will be cross magnetizing plus demagnetizing. Basically it will reduce the flux. Now if it is reducing the flux, what does actually it means? If it is reducing the flux, basically your XAR will be greater than 0, right? Because what is it? I have to provide some flux. So whatever flux initially it was developing, some of it is getting reduced to this armature reaction, right? Same as case of leakage reactance. In leakage reactance, what used to happen? Whatever flux I was producing, some of it used to go away due to leakage, right? That's why this XL was positive, right? Same thing will happen here. XAR will be positive because this is demanding some flux, right? Because overall flux is reducing. So this is demanding some flux. So XAR will be kind of positive. So basically your excess, right, will be positive. So now let's draw the phasor basically, right? So this is my current IA which is lagging. If it is lagging, So I have to draw out few things. Okay, so let me first do this, that uh, okay, this is my VT angle, right? So what is my E equals to? So E E is equals to, we have all, yeah, E is equals to this value, right? E is equals to this value. So if E is equals to this, so let's assume that your VT is somewhere around here. This is your VT. Okay, VT is VT angle 0. This is your reference, right? So as it is a lagging load, so the current will lag, right? This will be your IA. I'm exaggerating it to provide the phase angle to be more higher. This is your current IA. This is your current IA. Now, what will be the drops basically? So the drop, this IA into RA will be in phase. Will it be in phase with VT? Yes, it will be in phase, right? Because this is the theta angle, yeah. So this will be in phase with the drop VT. So this will be my IA into RA. Now there will be another drop. There will be another drop. What is the other drop? So I will break this down. Now, as I am telling you, excess is positive. Excess is positive because the flux is reducing. So it is like a reactance drop, right? So it will be plus J into XS. So if this is simply I into RA, plus J into XS will be somewhere around here. This drop will be called as plus J into XS. Am I correct? Yes. Yes, I'm correct. So just thinking about something. IA into RA, yes. Okay, sorry, I have to add with VT, right? I have to add with VT. So this should be added with VT. Okay, sorry. So here, right, this will be added actually. Here it will be added. So this will be flipped here, IA into RA. Okay, sorry, again, what I myself have forgotten totally the phasors. Sorry. So basically, right, I have to add this with VT. So this does not have any phase shift. So IA RA will be somewhat like this. It will be parallel to IA, and this will be the drop basically. This will be the drop, right? Yeah, IA into RA. So all this is just phasor, right? All this is just phasor. And then basically there will be, excess is positive, there will be a drop due to the synchronous reactance. Let's write this as J into IA into excess. It will be 90-degree, what? It will have a 90-degree phase shift from the IR, right? In the, okay, it should be in the anti-clockwise direction. Yeah, this is the direction of IA. So 90-degree will be this, right? So J IA into excess. Now, if I connect this initial point with E, right? So let me use another color. So this will be my basically resultant EMF, okay, E or EF, whatever you want to say. Now let us understand few more angles. So this, the angle between the VT and E is known as the delta angle, right? So this is the delta basically. This will be the delta. This will be the delta. And one more angle between the current IA and E. What is the angle between the current IA and E is known as the internal power factor angle. So this is known as the, this is known as psi basically, psi, which is actually known as the internal power factor angle. internal power factor angle. So we got three angles. So delta is the angle between the terminal voltage and the voltage in the developed in the armature windings, right? So also known as the power angle or the torque angle. Why is it called power angle or torque angle? That we will understand when we will understand about the when we will learn about the power flow. Okay, and your theta is known as the power factor angle, normal power factor, load power factor. Okay, angle between the load voltage and load power factor angle, terminal voltage and the load current. Okay, so we have got three angles. Okay, I hope you have understood this basic point. So what is your psi actually equals to? Psi, the internal power factor angle, is actually equals to theta plus delta. That is what my psi is equals to. Okay, same thing is written over here, done over here. Basically, this is my Vt, this is my delta, this is my theta, this is my psi. Now I want to derive few values. Okay, so when there is no load connected, when I is 0, basically my EF and V are same. Basically, there is no active power getting developed. Hence, that's why no current is flowing. Okay, that's why no active power is there. So sine of delta or sine of 0 is 0. So there is no torque getting developed. Okay, if I is non-zero, then this relationships will be there. Okay, now let's try to understand, like, how can I find out the magnitude of E? How can I find out the magnitude of E? That I want to know. Okay, so what we can do is we can actually break this Vt component. We can break this Vt component along two directions. So this Vt component, okay, not this Vt component actually. Can I break this? Okay, yes. Because I want to find out the value of E. How can I find out the value of E that I want to know? Basically, I want to find out the magnitude of E with respect to Vt and Ia and cos phi. How will I find it out? That is what I want to know. Okay. Okay, this is V. This overall thing is V, right? So this is theta. This is theta. So V cos theta, V sin theta. Okay. Yeah. So basically what I want to understand, this is I, right? So if I draw this here, so basically, right, I want to draw this triangle. So this is my E, right? This is my E. E is a combination of both Vt and IARA, and your what do you call Ia jxs, right? So this Vt also can have two components, right? So if this is theta, this also will be kind of theta. This is the angle between the Vt and Ia. So I can break this down Vt in two components. One will be this component, Vt cos theta. Another one will be the 90-degree component known as the Vt sin theta. Okay, so basically it is like a triangle. So what will happen? It will be like a triangle. So here the base of the triangle will contain Vt cos theta plus IRA, because if you see, they are just parallel, right? This drop was IRA, this drop here was IRA. So this Vt cos theta and IRA are parallel. Okay, so this will be parallel. So this will be Vt cos theta plus IRA, and the 90-degree component will be Vt sin theta plus Ia xs. Okay, and this will be the overall E, right? So now you can overall find out the value of E. What will be E? So by Pythagoras theorem, I can directly say, like, the magnitude of E will be under root of Vt cos theta plus IARA whole square plus VT sine theta plus IA excess whole square. Now this is for a lagging load. What will happen for a leading load? We will see that. Okay, we will try to understand what will happen. For a lagging load, it is very easy to understand because here the armature reactance and the leakage reactance both are in the same direction. Both are having demagnetizing effect. Okay, we will try to see that. So this will be the value of E. Okay, and how will I find out the internal power factor angle tan phi? What is tan phi? So tan phi is this angle, right? This angle. So which is this angle phi? Correct. So tan of phi, which is equals to theta plus delta. Very important. These things are very important, right? This numericals can be asked from here, right? They can ask you internal power factor for a lagging load. So it will be theta plus delta, which will be equals to height upon base, right? So height is Vt sine theta plus Ia excess divided by Vt cos theta plus IRA. Okay, so this will happen basically. This will happen. So like this, you can find out the internal power factor angle, also the magnitude of EMF, induced EMF. Okay, remember all these are with respect to lagging load. Okay, this phasor diagram is with respect to a lagging load. What will happen for a leading load? We will discuss about that. I will just bring the circuit here. Okay, what will happen for a leading load? For a leading load, things can be a bit different. Okay, so for a leading load, remember your leakage reactance will be negative basically. Sorry, your synchronous reactance will be negative. Why? If you remember, this was my flux, main field flux. This was my MMF, FF. This was my induced EMF, EF, due to the main field flux. And as it is a leading load, what will happen? So your armature current will be somewhere here, right? IA will be somewhere here because current will lead the voltage, induced voltage. So as it is leading, bit part will be cross magnetizing, right? That I don't care about that. And some of it will be magnetizing, right? It will have magnetizing effect. So how can I represent magnetizing effect? Okay, how can I represent that the overall flux is increasing? So if you see here, the overall flux was reducing. How had I represented it? Simply I told you that I modeled it with a simply inductive load, right? Because inductance takes the flux, right? Inductance takes the flux. Okay, it does not develop flux, right? It takes the flux. So as the flux was reducing, this reduction in the flux I modeled using inductive reactance. Now I have to model increase in flux. How can I model increase in flux? I will model it with a capacitive reactance, just the opposite, just the opposite. Okay, very important. Trust me, you go and watch any video in this whole industry, right? In this whole industry, you go and watch any video, any paid content. Nowhere they will explain you this. Nowhere they will not explain how am I modeling the increase in flux. They will just say it will be negative. Okay, assume it is negative. That's it. Now basically, my armature reaction this time will be negative. Now one thing you have to keep in mind, overall your synchronous reactance now will be basically, as initially synchronous reactance we assume to be positive only. So it will be a combination of the leakage reactance minus the armature reactance. Okay, why minus? Because your armature reactance is negative. Sorry, if I write negative here you will get confused. Okay, let me write plus only here, right? But remember your armature reactance is negative. So basically your synchronous reactance is reducing. Now you might have a doubt, so synchronous reactance can still be positive because XL is a positive quantity, right? XL will be always be positive because it is a leakage reactance of the winding, that will always be positive. But XAR is negative. So what will happen, sir? So here your synchronous reactance will still be positive, still it will behave as inductance only, but it will reduce basically. Synchronous reactance will reduce. So the drop will be much smaller. Here, if the drop was much larger, the drop here will be much smaller. So this plus J, like because the leakage reactance is still there, right? So plus J into IA into XS will be much smaller. This will reduce drastically. Okay, so basically what is happening over here is that I can say that the magnitude of IA into XS is much smaller in case of a leading power factor load than magnitude of IA into XS in case of lagging power factor load. Okay, so how will I draw the phasor diagram? So phasor diagram will be something similar only, but there will be minute differences. So let me first draw the this VT. So VT is here. VT will be here. Like I will draw the phasor diagram again by following the same equation. What was the main equation? This was the main equation, right? Where did it go? Yeah, this one. I will still follow it. I will not forget it. Okay. So here, what will happen? This will be VT. This will be IA. This will be theta. And now what about IARA and all those things, right? So VT plus IRA. So this will be in parallel with here. It is leading, right? It is leading, hence I have drawn current as leading from the voltage. It's a leading load, right? Current is leading from the voltage. So I will draw the IRA drop. So this will be IRA drop basically. If I am able to reduce the size without changing this angle, right? This will be the IRA drop. And what will be plus J into IXS? XS is lower right now. So plus J, again I will have to make it in the anti-clockwise direction. This will rotate in the anti-clockwise direction. Why? Because it is plus J, right? That is why. Okay, let me take it again and let me move it, rotate it by plus 90. Yeah. So this will be plus 90. And this drop will be much lower. Much lower. Okay. So this will be my IRA. This will be my JIA into XS. Drop is much lower right now. Okay. What will be the resultant voltage? Resultant voltage will be this. This will be the resultant voltage. Okay. So now what is the internal power factor angle? The internal power factor angle is this, right? Psi. What is it equals to actually? So what is delta? Delta is the angle between the resultant voltage and the terminal voltage, that is delta. So what is psi equals to? So psi this time will be equals to theta minus delta. Okay, psi will be equals to theta minus delta. That is what my psi is equals to. Okay, I hope you have understood this thing. So let's now derive the expression for this, the value of the E, magnitude of the E, and the value of the psi. How can I find out the value of the psi? So I will copy this. I'll copy this, and this Vt will have two components, right? One will be again Vt cos uh, cos theta. Okay, there will be two components. One will be Vt cos theta and Vt sin theta, right? That will be perpendicular basically. It will be somewhere around here. Okay, now these are all dot dot. So this component is Vt cos theta. I don't know what is the length currently, which will be somewhat lower than Vt. This will be Vt sin theta. Okay. Also, if I want to add this, right, this will be parallel with IRA, because Vt cos theta is parallel with IA and IRA also is parallel with IA. So I can simply add these two components. Correct. I can simply add these two components. So I will get my E basically. I want my E, right? Also, my Vt sin theta, I can copy it and paste it over here, right? So basically it will basically touch here. It will basically touch somewhere around here actually. The length I have not properly written it. The length of the Vt sin theta will be touching somewhere around here. Actually this is not totally correct. Actually, yeah, this length should reduce more. So basically what should happen, this should come here, right? It should absolutely come here, because it is completing a triangle. So basically what do I mean? So it should complete a triangle, right? Yeah, basically it should complete a triangle. So it should be, yeah, it should be somewhere around here. This should be the length, and this should be the length of Vt cos theta. Okay, it should basically complete a triangle, right? It's a right angle triangle. Vt is here. This will be the x axis component. This will be the perpendicular component, right? Parallel component, perpendicular component. Okay, and so I can again copy this thing, right? I can again copy this thing here. So now, okay, now it is exactly matching. So I was doing wrong here. This triangle thing I was doing wrong, right? So basically it should be a Pythagoras triangle. Vt is here. This is theta. So it will have a base component. This will have a perpendicular component. This will be what? This will be my Vt sin theta, and this length will be Vt cos theta, right? This whole thing, this length. Now this E also has two components. If you see, if I do E cos psi, it will be this one, right? This value. So this is this will be basically E cos psi, correct? And this length, right? This length will be, now remember this is not correct actually. This, right, this is not correct totally. So my Vt sin theta is this much, correct? Vt sin theta is this much, right? Okay, let me do this. And my this is my E sin phi. Okay, so this is my E sin phi, this is my E cos phi, right? So what is, like, ultimately I want to find out E. So what will be E? E will be basically E will be under root, this we had already done actually in the previous one, but there I did not explain it in detail, so here I am explaining it in detail, right? E sin phi whole square plus E cos phi whole square. Okay, so what is your E cos phi and E sin phi? So E cos phi, E cos psi is basically Vt cos theta, this component, plus the remaining one, that is IRA, right? This is the IRA. So Vt cos theta plus IA RA, and your E sin phi, E sin psi, not phi, equals to Vt, this whole length, minus this length, right? IXS. So this will be Vt sin theta minus IAXS. XS is positive number, okay? Here XS is positive. So remember, we are subtracting it, okay? So from here I can easily find out my E. So E will be basically under root of Vt cos theta plus IARA plus Vt sin theta minus IA XS whole square. Okay. So now this is my magnitude. This is my magnitude expression for magnitude. What is my tan psi? Tan psi is equals to simply the ratio, right? This over this. If I take the ratio, I will only be left with tan psi. So this will be Vt sin theta minus Ia into XS divided by Vt cos theta minus Ia into XS. Sorry, plus Ia into Ra. So do you need to remember this formula again? Like previously we had derived a formula here, right? I had derived a formula here. Do you need to remember it again? No, right? So what you do, you remember this. You remember this formula. Okay. Obviously we don't have too much time to draw the phasor. You remember this, right? In this formula it's very easy to remember. Everything is positive. Everything is positive. Okay. But here what you do, because remember your theta is negative now. Theta is negative because theta is measured with respect to Ia. Now voltage lags the current, or current leads the voltage, so theta is negative, right? So what you will do, in the previous formula you will replace with theta from in the previous formula to derive the expression for a capacitive load. For a leading load, you replace the theta with minus theta. Okay, that's it. Everything will be sorted. You replace the theta with minus theta, everything will be sorted. How? Because if you replace with minus theta, this will still be Vt cos theta only. Cos of minus theta is cos theta. This will be IRA, no change. This will be Vt minus sin theta, because sin of minus theta is minus sin theta. So this will be negative. Still it is positive, right? Plus Ia axis in the previous formula. So I will just copy this previous formula. Still it is positive and this is negative. So basically if I ask you a minus b whole square, is it equals to b minus a whole square? Will you agree on this if both are real? Of course it is same, right? If I am squaring a minus b or b minus a, it is same. It is same as saying 3 minus 2 whole square is equals to 2 minus 3 whole square. Is it same? Yes, it is same, right? So you can do it, no problem. So same thing we are doing, 2 minus 3 whole square, right? Here also what we will do is, here also we will replace the same. Here what we will do is we will replace theta with minus theta here. So this will be minus Vt sin theta. This will still be plus Ia axis. This will be Vt cos theta plus IR. Okay. So here, right, one problem will be there. Your psi will come out to be negative, which is fine. if psi comes to be negative, that basically means that you have to go in the clockwise direction from E, right? If your psi is coming positive here, if your psi is coming positive, that means your E is where? Your E is here, right? E is here. Okay, sorry. Your okay, sorry. Your psi is coming positive. Okay, what? Okay, one thing we cannot do always for this, right? We cannot simply replace theta with minus theta. This will mess up actually. This will get messed up. Or okay. Don't do this actually. Don't do this. What you do, right? You this is another formula, right? Basically, your tan. This unfortunately, okay, no. This is tan theta plus delta. This will work if I replace theta with minus theta. Kind of yes, yes, it will work. So what I'm telling you is, what you do is, okay, I'll tell you in new page. What you'll do, you will just replace theta with minus theta, okay? Or if you want to remember, you can remember it, no problem, okay? But I'm telling you a shortcut. So let me go back to the previous formula. So here, right, if I replace theta with minus theta in this formula, so don't write it in terms of psi. That is the one mistake that you will do. You'll write it in terms of psi. Don't write it, okay? So here, right, if I replace theta with minus theta, what will happen? This will be magnitude of A. This will be Vt cos of minus theta, which is cos theta only, plus Ia whole square. This will be minus of Vt sin theta plus Ia xs whole square. Okay, this can be rewritten as Vt cos of theta plus Ia whole square plus, this will be like, I can rewrite this as Vt sin theta minus Ia xs, which is already what we derived here, right? Same thing, we derived it here. Okay, now what about this one? So this is equals to what actually? This is equals to tan of psi, tan of theta minus delta. If you see here, still my E is leading Vt, right? Because then only the active power will go. So this is tan of theta minus delta. Same will happen over here, right? Same will happen over here. That if I replace for in the angle formula theta with minus theta, this will be tan of minus theta plus delta. If I replace here theta with minus theta, this will be minus of Vt of sin theta plus Ia xs divided by Vt of cos theta plus Ia Ra. Okay. So one thing you have to understand is that my tan of minus theta is equals to minus tan of theta, right? So if I take negative sign common here, and if I multiply minus 1 on both sides, this will be minus of tan of minus theta plus delta equals to Vt sin, I am taking the negative sign common, this will be minus Ia xs, right, divided by Vt cos theta plus Ia Ra. Okay, now I know this minus tan theta is equals to minus of tan theta. So I can take this negative sign inside. So this will be tan of theta minus delta equals to Vt sin theta minus Ixs. Okay. Plus Ia R. Okay, so it is same as this one, right? Same whatever we have derived here, same thing, nothing has changed. So ultimately that is a factor. If you want to remember, you can remember, just replace theta with minus theta and everything will be sorted. Just remember this formula and replace theta with minus theta and everything will be sorted. You don't have to remember anything separately. Now if it is unity power factor, then there is no factor of theta, right? Then how will the phasor diagram be? So again I will copy this, right? Again I will copy this equation. This equation will always be valid no matter what. Now if it is unity power factor, the value of xs, right, will not change. So here, right, the drop was very high. This this drop, if you see, was very high. Why it was very high? Because the overall effect if you have seen, the flux overall reduces. If the flux reduces, that means more flux is leaking out. Resultant flux is reducing. If resultant flux is reducing, xs will increase, right? This will increase. Hence, that's why, if you see, that's why the drop here is very high, very huge drop, right? Xs is very high. Synchronous reactance will be very high. In case of leading loads, the synchronous reactance will actually reduce due to the armature reactance having capacitive behavior. In case of unity power factor, the synchronous reactance value will be moderate. Okay, synchronous reactance value will be moderate as it is written over here. Okay, synchronous reactance will be moderate. So Xs will be moderate. Okay, so what I can say is, here Xs is moderate. So basically this will be my Vt. This is my Vt. And my Ia also will be in the same phase, right? Because it is unity power factor load. Ia also will be in the same phase. Now what will be the drops basically? So this will be my IARA drop. IARA drop. Okay, and 90-degree shift to this will be my IAJXA drop. Okay, and my E will simply be this. This will be E. This will be my J IA XS. This will be my IRA. Okay, and this will be my delta basically. Theta is 0, right? This time theta is 0. So what is psi? Psi is also this only. So luckily theta is 0, so psi is this only. So psi in case of unity power factor load is equals to delta only. Okay, so again, like, it is very simple now, very simple to understand. What will be E? Magnitude of E, it will be under root of this thing, Vt plus IRA. There is no cos theta because theta itself is 0. So Vt cos theta is simply theta equal to 0. Vt plus IRA whole square plus Vt is not there. There is no perpendicular component of Vt, only Ia XS. So Ia XS whole square, and the tan phi or tan psi, sorry, to be precise, will be basically this component Ia XS, the perpendicular upon the base, Vt plus Ia Ra. So what is the shortcut? Shortcut is, again, you replace theta with 0. So here, right, in this formula, if you replace theta with 0, what will happen? This will be Vt only, cos 0 is 1. So this is Vt plus IRA, sin 0 is 0. So this will be IXS. So this is sorted. Okay. Here if I replace theta with 0, this will be tan delta, right? This will be 0. So this will be IXS divided by Vt plus IRA, which is exactly what I have written over here. Okay, so that's how we do. So you just remember this formula if you want to, and then you replace theta. For leading power factor, you replace theta with minus theta, and for unity power factor, you replace theta with 0. Okay, so that is what you have to understand over here. So few key points I want to say here. One key point is I can clearly observe that the magnitude of E will be greater than the magnitude of Vt, right? Because I'm adding some components, then I'm squaring, then I'm adding. So this is clearly observable that the magnitude of E will be greater than magnitude of Vt for unity power factor. For for lagging power factor, will it be true? Will it hold true? For lagging power factor, what was the formula of E? For lagging power factor, the formula of E was this, right? Everything is positive here. So again, I'm adding, like, what is happening if I square this, right? If I square this, what will I get? So I want to do some mathematics here. So this will be, if I break it down, this will be Vt whole square plus cos square, here Vt whole square plus sin square, so ultimately that will become Vt square only. Sin square theta plus cos square theta is 1, plus this will be 2 Vt cos theta into IARA plus 2 Vt into sin theta into IAXS, plus this will be IA square into RA square plus XS square, that is basically ZS whole square. Okay, very basic thing. Basically my Z, right, is what it is, the magnitude of RA whole square plus XS whole square, right? That's what I'm written here over here. So a component will come, that will be IA square XS square plus IA square RA square. So if I combine IA square, this will be RA square plus XS square, that will be Z square. So I'm observing that this is my E, magnitude of E, right? So I'm observing, I'm adding Vt square with all these components, these are all added. So here as well, the magnitude of E always will be greater than the magnitude of V. Very important point to understand. But here, right, the magnitude can reduce in case of leading power factor. So this will be for the lagging power factor. Okay. So for leading power factor, what will happen? Now if I break this down, right? If I break this down over here, what is the formula? The formula is here, right? This is the actual magnitude of E formula. So if I break this down, if I break this down, so I can write my E is equals to, again, Vt whole square cos square theta plus sin square theta, it will be 1 only, Vt square only, plus this time this will be 2 Vt cos theta into IRA minus, again this is minus, right? So this will be minus 2 Vt sin theta into IA XS. Again this will be plus, because this will be IA square RA square, this will be IA square X square, which will be plus IA square ZS whole square. Now I cannot say certainly that the voltage will be, the magnitude of voltage will be greater than the magnitude of the Vt. Okay, cannot comment. Okay, it can be anything. Why? Depending on the value of this 2 Vt sin theta IXS, right? Depending on this value. If this value is very high, then I'm subtracting, like if let's say this is very dominating compared to these two values, then I'm subtracting from Vt square. So then this will be lower, then my magnitude of E will be lower than Vt, right? If this is low value, if this is some, like the magnitude of this is small, then these are dominating, then the E will be greater than the Vt. Okay, so For leading loads cannot comment. Okay, very important and key point to understand. Other guys will just tell you directly that for leading loads, you remember that magnitude of E will be lower than Vt, but not always. Not always, because these components are there, right? These things are there, these positive components are there. So just be careful regarding this. It will not always be the case that the magnitude of E will be lower than Vt. It can be higher as well depending on this value. Okay, depending on the values. I cannot comment directly over here. Okay. So let's now solve few questions. So I will show you the questions, try it out by yourself, then I will come back with the solution. This is the first one, this is the second one, this is the third one. Okay, only 3 questions we will do. I guess more questions we have, no, 4. Okay, 4 questions we have, 5 questions we have actually. This is also another question. So this 5 questions we will do. Try these questions out by yourself and I will come back with the solution. So let me start with the solution over here. So this is the first question basically. So in this question we have a 3-phase 10 kilovolt 400 volt 50 Hz star connected alternator delivers its rated power at a power factor of 0.8 lagging. So cos theta is 0.8 and it is lagging. Given that the armature resistance is 0.5 ohms, it is a 10 kVA load. Okay, 3-phase 10 kVA. Determine the torque angle. So they want me to, and the synchronous reactance XS is 10 ohm. They want overall synchronous reactance XS is 10 ohm. They want me to determine delta. How can I determine the delta? So it is operating, delivers its rated load at this power factor. So it is operating at rated load. Can I find out the rated current? So I know that P rated is equals to, for a 3-phase load, it will be root 3 into V line into I line into cos of phi, cos of theta. Okay. So from here I can easily find out the rated current IL, that will be equals to the armature current only. So P rated is given to me as 10 kVA. Okay, this is given in what? This is given in volt amperes, right? This is not active power, this is apparent power. So I don't need to write this directly. What I can write, instead of cos phi, I can directly write that my S rated will be root 3 into VL into IL. So I can just neglect the cos phi, cos theta, correct? So IA will be equals to 10 kVA divided by root 3 into VL. VL is 400. Whenever a voltage is mentioned, you have to assume it as line voltage unless and until specified. Okay. So this will be VL. So from here I can easily find out the rated current, full load rated current. So my full load rated current, if I want to calculate, uh, 100 divided by 4 into root 3. So 14.43 amperes. This will be the rated current. Now, am I corrected? Am I missing a point? So this is 100 upon 10 kVA 400 volts is root 3. Is correct, right? Yeah. This should be 20 gets cancelled. This is 100. Yeah, 100 upon 4. Yeah, 14.40. Yes, correct. So now let's basically write the formula. Okay, what they're asking me to find out the angle delta. How will I find out the angle delta? So you can use the formula or you can solve by basics as well, whichever one is suitable to you. So they are asking you to find the delta, which will help me find delta. So I know one thing, right? What do I know? I know this formula, tan of psi. It is a lagging load. Tan of psi is equals to Vt cos theta plus ia, sorry, this will be going in the denominator. How do you remember that which will go in the denominator and which will go in the numerator? So it's a very basic trick that you can use, is cos always goes in the denominator for a tan, okay, and sine always goes in the numerator for a tan, right? That's how you remember that which one will go in the denominator and numerator. And with sine always excess will be there, and with cos always the real component, that is RA, will be there. With sine the imaginary component will be there, with cos the real component will be there. So this is how you can remember the formulae. Okay, and what is psi equals to? So bit of it, if you just draw the phasor diagram, this will be my Vt, okay, my Ia will lag and my Ea will be somewhere around here, right? This will be my Ea. So if you remember, this was the psi and this was the theta, so your delta will be basically psi minus theta. Okay, if you ever tend to forget, you just draw the things, everything will be memorized, like everything you will be able to recall. Okay, so now I will solve this. So Vt I already know, terminal voltage. What is the terminal voltage? Remember, the terminal voltage here is not 400, okay, per phase equivalent, whatever you have to write, per phase equivalent. So it will be 400 divided by root 3. What is sine theta? Sine theta is 0.6 because cos theta is 0.8 plus Ia is 14.43 into excess is 10 ohms, right? 10 ohms divided by Vt cos theta plus Ia 14.43 into RA is 0.5. Okay, so if I just calculate the values, 400 divided by root 3 into 0.6, so this will be 138.56 plus 144.3 divided by, this will be 400 divided by root 3 into 0.8, 184. So this will be 14.43 into 0.5, 14.43 into 0.5, this will be 7.215. Okay, so this value comes out to be 138.56 plus 144.3. This comes out to be, okay, this is not here, this should not be here, this value should be 282.86 divided by 184.75 plus 7.215, this will be 191.965. okay, so now if I take the ratio of these two, 282.86, and take the tan inverse, so tan inverse taking, it will be 55.367, almost 58.837 degrees. So what will be basically my sorry, this is this is not the value, actually this is the psi angle, right? Psi angle. So psi angle is this, right? And your tan psi is 1.474. okay, so what is my theta, sorry, what is my delta? Delta will be psi minus theta, as discussed we have here, right? As we have discussed, that is my delta. Theta is what? Theta is basically, theta is cos inverse of 0.8. 0.8. okay, so cos inverse of 0.8, that will be 36.87. okay, so from here I can directly find out what will be my delta. Delta will be basically psi is 55.837 degrees minus theta, so 55.837 degrees minus theta, so it is basically 36.87 degrees, so it will be 18.97 degrees. okay, so this will be the value of the delta actually. So remember, if they have not mentioned, right, angle they are asking, determine the load angle. If nothing is mentioned, actually, you should assume it to be in radians. Okay, if nothing is mentioned, by default you will assume it to be in radians. So in radians, what will be the value? So in radians, this into pi divided by 180, this will come out to be 0.331 radians. Just be careful regarding this angle thing, right? In numerical answer type, you can go wrong. Okay, what is the other way to solve this? So this was the method 1 using the formula. What is the method 2? So method 2 is very simple, right? Method 2 is directly solving the circuit. So I know this very basic phasor equation. E will be equals to E angle delta will be equals to Vt angle 0 plus Ia into Ra. Ia is what angle? Ia is angle minus theta, because it is lagging, that's why negative angle. Ra plus j xs, right? You solve it. So your Vt is what? Vt is 400 divided by root 3. What is your theta? Theta is 36.87. Your Ra is 0.5. Your xs is 10 ohms, right? Your Ia is 14.43. So all these values you'll put in here, right? And from this, if you solve this equation, you'll get a magnitude of E and a angle, right? And that angle will be basically your power angle or delta. Okay, so I hope you have understood the method 2. Method 2 is using basic equation, okay, standard equation, but this will be time consuming, right? So that's why we remember this formula to save our time. Okay, let's now solve the next one. So a 5 MVA 11 kilovolt, so it's a 5 MVA. Again they have given the rating in apparent power. Just be careful regarding this. So it's a 5 MVA 11 kilovolt. So Vt will be what? 11 kilovolt. It is a star connected. If nothing is mentioned, by default you will assume star. If it is star connected, so your per phase voltage will be what? Per phase will be 11 kilovolt divided by root 3. Is synchronized with the bus bars and operates with an induced EMF to 125% of its rated voltage. So the induced EMF E is 1.25 of its rated voltage Vt. When is it possible? When is the induced EMF can go higher than the rated voltage? When it is possible? It is possible only in case of leading loads. Possible. Otherwise, okay, no. Sorry. What I'm doing? Induced EMF operated with an induced EMF. Sorry, it is possible in all kind of load. Sorry, it is possible in all kinds of load. So its induced EMF is equal to 125% of its rated voltage. Okay. If the alternator supplies a load current of 500 amperes, determine the power factor. Assume the synchronous reactance is 5 ohm per phase and armature resistance is negligible. So they are telling me that my E is 1.25 times Vt. I don't know whether it is lagging or leading. Okay, I don't know whether it is lagging or leading. Okay, only they have given me this equation. Is this equation helpful? Basically, the magnitude of E will be 1.25 times the magnitude of Vt. Okay, so now what I can say, I again know this formula. What is the formula? Formula of magnitude of E is what? It will always be same no matter what. So let's first assume, assume lagging load. Then we will see if our assumption is correct or wrong. Okay, so this will be, what was the formula? Vt cos theta, Vt cos theta. This formula will always be true, plus IRA. Ra is 0 here, so I will not write it, whole square. Vt sin theta plus Ixs whole square. Okay. So how do I find out the power factor angle? So one thing I know is, how can I derive it? Okay. Do I know IA? Okay. What else? It is delivering 500 ampere. So I know what is my armature current. IA is 500, right? So if I rewrite this equation, right, this will be basically Vt square plus uh, 2 Vt sin theta Ia xs plus Ia into xs whole square. Okay, this is on the whole under root. So if I square both sides, right, so what is magnitude of E? Magnitude of E is simply 1.25 of Vt. So if I square both sides, this will be 1.25 of Vt whole square equals to, this will be Vt square plus, what is Vt actually? Vt is 11 kilovolt. So I will keep it in kilovolt only. I will keep everything in kilovolt. I will keep everything in kilo. Remember, I will keep everything in kilo for my own convenience. This will be 11 kilo divided by root 3 into sine theta. I have to find out sine theta. I don't know what is sine theta. Into Ia into xs. Ia is how much? Ia is 500 into xs. Xs is, I guess, 10 ohms, right? It is, yeah, 5 ohms. Sorry, not 10, 5. Plus, remember, I have to keep everything in kilo, right? So this will be 500 into I into x is again 5 whole square. So I will divide this by 1000. Why? Because I have to keep all the quantities by kilo. This is also in kilo. Vt is also in kilo only. Okay, just be careful regarding that. So this will be basically, this Vt square will go here, and this also will go here. So this will be 1.25 whole square minus 1. So this will be 0.56 25 Vt square and minus this value, right, whatever this value is, 2.2.5, sorry, 25 into 10 raised to power 4, 25, basically this will be 625 into 10 raised to power 4 divided by 10, 1000, this will be this much only. Okay, this is equals to basically 2 into 11 divided by root 3. Okay, this again is 25, 10, 5000, right? Into sine theta. Okay, so Vt square, Vt is 11 divided by root 3 into 0.5625. This will be 22.625. Okay, this is quite large. Okay, something is gone wrong. Okay, something definitely okay, something definitely is kind of wrong over here. It is negative. It is coming out to be negative. Okay, certified it. So this is 500 kilo, right? Kilo should be there. 5 into 5, 25, 25 whole square, 10 raised to power 4, 625 into 10. Okay, quite large value this is. Okay, sorry. So what I'm talking about, sorry, Vt square is what, like I'm squaring in this, right? So kilo whole square, what will be 10 cube whole square? It will be 10 raised to power 6. I'm sorry, that is what I'm making the mistake. So everything will be in mega. Sorry, I'm really sorry. So here also, this is already in kilo. This also have to divide by 1000 to convert it into mega. Okay, and that's why you need to be careful here. Just you need to be very good with units. So I have to divide by another 1000 to convert it into mega. Okay, so this will be divided by another 1000, and this also will be divided by another 1000. Automatically this 10 cube will go away. right? This will go away, only 5 into 11 will be stayed. Okay, so I'm just writing everything in mega, that's it. So this will be 100.625, right? So this will be 6.25, so this will be 16, remember this is 16.475 is equals to 5 into 11 divided by root 3 into sine of theta. So your sine theta is equals to into root 3 divided by 55 is 0.517. Now if you see, your sine theta is coming out to be positive. If your sine theta is coming out to be positive, that means whatever you have assumed is correct. If it was negative, that means your load was actually leading, that's it, right? If theta is positive, like you have assumed for a lagging load where theta is positive, so which is coming positive, that means your assumption was correct, it is a lagging load only. Okay, lagging load only. If you would have assumed it to be negative, what changes you would have made? Only here a negative sign would have been there. If a negative sign is here, then this, all this will be same, just this will be negative, this will be negative. If this is negative, what will happen? This will be still positive, right? And still on the right hand side I have a negative. Automatically your theta will come out to be negative. So if you would have assumed it to be a leading load, then the theta would have come out to be negative. That means your initial assumption was incorrect, right? If your theta comes out to be positive, so whatever was your initial assumption, that was correct, that the load has to be lagging. But if your theta comes out to be negative, that means your initial assumption was wrong, because the sign, while writing this formula, the sign of theta was already taken care of. Okay, so if your theta is coming out to be negative sign, that means your assumption is wrong. Okay, here theta is coming out to be positive, so our assumption, initial assumption was correct. So theta is positive, theta is positive, that means our initial assumption was correct. Okay, so what is the theta then? So what are they asking? They are asking me the power factor. Power factor will be what? Power factor will simply be cos of theta. So for that, first of all I have to calculate the theta. What will be theta? Theta will be sine inverse of this, that comes out to be 31.175 degrees, and cos of theta will be 0.856 lagging. Okay, so this will be basically the answer of this question. Very simple and easy to understand. Okay, let's now solve the third question, right? A three-phase alternator supplies power to a balanced three-phase load operating at power factor 0.07 lagging. So cos phi is 0. Cos theta is 0.707 lag. Okay, it is operating at balanced load. It is observed that the open circuit EMF phasor leads the corresponding terminal voltage by 15 degrees. So basically by this, right, open circuit EMF phasor leads the terminal voltage by 15 degrees. It basically means that the induced EMF leads the voltage phasor by 15 degrees. So they have just given me the value of delta. Okay, delta is 15 degrees, and I know normally the induced EMF leads the voltage, so delta is positive, which is 15 degrees. Okay, assuming negligible harmonic effects, determine the electrical angle between the main field MMF axis and the armature reaction MMF axis. Okay, how do I solve it? So I know this will be my phi f, correct, and phi f will have the main field MMF FF, and this will be my EF. This will be the no load voltage. Now they are telling me that the no load voltage leads the terminal voltage by 15 degrees. So the terminal voltage will be somewhere around here. terminal voltage will be somewhere around here. Okay, so now what I can say is also they are telling me that the power factor angle is 0.707 lagging. That basically means that the theta will be 45 degrees, negative 45. Why negative? It is lagging, right? So the current will lag the voltage, terminal voltage. So current lags by 45 degrees. So the current will be somewhere around here. Minus 45. Current will be somewhere around here. This will be the current IA, right? So this is the 45 degrees basically. Okay. So it should be somewhere around here. So now the important point, let me not make it this much down, let me make it here. Important point is, now they are asking me what will be the direction of the field flux. So what will be the direction of the armature flux? Same along the armature current, right? Because my flux is what? My flux is mmf, is proportional to mmf, and mmf in turn is proportional to current. Same direction. So mmf also will be in the same direction here. This will be the mmf, that is f armature mmf. Now they are asking me what is the angle, electrical angle between the main field flux and the armature field flux. So the electrical angle will be this angle plus 90. This angle plus 90. What is this angle? 60. So this overall angle is 60 and this is 90. So the angle angle between the FF and FA is equals to 150 degrees. Okay, angle between FF and FA is 150 degrees. Okay, so this is the angle that they are asking. So this is the answer basically. This is the answer. Okay, they are asking in electrical angle. They should have mentioned in degrees actually. In degrees, this will be the angle. This will be the answer. 150 degrees will be the answer. Okay, let's now solve like these questions, right? Trust me, these are considered as difficult questions. For other students, these are considered as difficult questions. For our students, this will be like a cakewalk. Okay, because I have explained every single thing with basics, right? So this will be cakewalk for you guys. So now let's solve the next one. So a synchronous generator supplying a load draws armature current at lagging power factor theta. Assuming leakage impedance to be negligible, determine the internal power factor angle psi. So the internal power factor angle, okay, not determined. So basically the internal power factor angle is psi, not determined, sorry, because we have to determine something else. The internal power factor angle is psi. So if I draw the phasor diagram, if you remember, for a lagging load, so this was my Vt, okay, and it is a lagging load. So okay, let me draw it proper only. So this was my Vt, this was my Ia as it is lagging, so it will be theta angle. So this will be basically it will have two components. Vt will have two components. One will be IRA, and this will be bigger, right? This drop will be bigger because the synchronous reactance will be very high. This will be Ia excess, okay, and this will be my E. So this will be my delta angle and this will be my psi angle, right? So my psi will be simply theta plus delta, that's it. Okay, so what they are asking, first of all, so they are asking me the angle by which the air gap excitation MMF lags or leads the armature MMF. Air gap excitation MMF basically means the field MMF, right? They are asking me the, okay, not the, yeah, air gap excitation. Whenever this air gap is written, right, this basically means the field MMF. So when armature current was not there, so this is the field MMF that they are talking about, field MMF. Okay, so this is my E, right, and the field MMF will lag the E by 90 degrees, right? So field MMF, field flux or MMF will be here. Okay, this is the air gap, and along this direction will be my basically my armature MMF, right? Same direction along the IA. So what is the angle here? So this angle is overall psi. This angle will be 90. So the field, they are asking me how much does the air gap MMF lead or lag. So the air gap MMF leads the armature MMF by psi plus 90. Psi plus 90. So it will lead by psi plus 90. So option A will be correct for the first one. For the first one, option A will be the correct answer. Psi plus 90. Okay. So what are they asking in the second one? The angle by which the resultant MMF leads or lags the armature MMF. So how do I find out the resultant MMF? So the field MMF will lead the induced EMF by 90 degrees, right? So what will be the angle of the resultant MMF? So resultant MMF, remember, is a combination of the armature current and the induced EMF. What is the combination of armature current and induced EMF? It is the Vt. So this also you have to remember, this I did not specify, that your resultant MMF will lead the terminal voltage by 90 degrees. How else can you understand? So you can understand it like somewhat like this. So this is my armature reactance impedance, right? And this was my no load circuit voltage. And if you remember, here I have this RA, JXS, and this was my ER, resultant MMF. So what is the angle difference here? If some current is flowing, what is the angle difference? Plus J, right? Plus J. So the resultant ER, and here they have told me to neglect the leakage impedance, and armature resistance also I will neglect. So basically, if I neglect these things, right? So basically my ER is roughly equals to Vt only. ER is roughly equals to Vt. So basically, actually what should have happened, because there will be some drop here, right? The FR, resultant MMF, that is the resultant MMF, will basically ER is the resultant voltage, right? Internal voltage that we have called. It will, so FR leads ER by 90 degrees, but in this case, as my ER is roughly equals to Vt, right? So I can directly say that the FR will lead Vt by 90 degrees in this case, because they have told me to neglect, the leakage reactance, and RA also I will neglect. Okay. So if that is the case, now they are asking me the angle between the resultant MMF and the armature MMF. Armature MMF is here, right? Resultant MMF is here. So what is the angle? So angle will be 90 plus theta. 90 plus theta, that will be the angle, and resultant MMF leads the armature MMF by 90 plus theta. So will lead by 90 plus theta. So option C will be correct. Okay. So in this case, it will be the option C. So resultant MMF will lead the armature MMF by 90 plus theta. Okay. Now let's solve it for the next one. So if I solve it for the next one, the angle by which the excitation MMF dash the resultant MMF. So excitation MMF is same as the air gap MMF only. Okay. So here they are just writing it in terms of different value. Excitation MMF is same as the air gap MMF only, air gap excitation. So whenever this excitation term is there, right, that means it is basically the talking about the field MMF. So now they are asking me the angle between the excitation MMF, that is the FF, and the resultant MMF and FR. Okay, not the armature MMF. So FR is here, FF is here. How will I find out this angle? This angle I need to find out. How will I find out this angle? So I know one thing, that this leads by 90 degrees and this FF also leads my E by 90 degrees. So both of them actually lead by 90 degrees, right? What is that angle difference between E and VT? That will be the same angle difference between FF and FR. Same angle difference between FF and FR. So the angle difference between the excitation MMF and the resultant MMF will be delta. It will be delta. It is just following the triangle rule. Basically, this angle difference is delta. So FR leads by 90, FF leads by 90. So both of them I'm shifting by 90. So this angle difference, phase difference will be still same. It will be delta only. It will not change. Okay. So it will still, sorry, actually this is kind of, okay, here, right? Okay, that's why the options are not correct. I have to change it. Actually, it is not MMF, sorry. This will be EMF. I'm extremely sorry. This will be the resultant EMF. So why does the resultant EMF like? I'm extremely sorry. Okay, that's why the options are here not matching, right? So here, right, this will be ER. Okay, excitation EMF and the resultant MMF. So FR and excitation EMF. Excitation EMF is simple E. Okay, excitation EMF is simple E, not ER, sorry. So the angle between the FR and E. So E is here and FR is here. So this whole angle is 90, right? This whole angle is 90. So what will be this angle? Basically, this little angle is delta. So this angle will be 90 minus delta. 90 minus delta. Okay, so FR leads the excitation EMF by 90 minus delta. But here, right, they're asking me the how much the excitation MMF leads or lags. So excitation MMF will lag because I'm moving in the clockwise direction from FR, right? So excitation MMF lags the resultant, sorry, excitation EMF lags the resultant MMF by 90 minus delta. So here it will lag by 90 minus delta, that is present in the option D. So option D will be correct. Okay, it lags by 90 minus delta. So option D will be correct. Okay, the angle by which the air gap MMF and the air gap excitation, again I think this is wrong. It is not MMF, sorry. It is not MMF. It should be yeah, it should be EMF. So the angle between the air gap EMF and the air gap excitation MMF, whenever this excitation term is given, that should be the hint that it is talking about the main field, right? And whenever just air gap or something is written, it is talking about the resultant. Okay, so here, right, previously I had told you wrong. If air gap is written with excitation, that means then it is called as field MMF. Okay, and if just air gap is written, that means it is talking about the resultant EMF. Okay, so they are asking me the angle of resultant EMF, that is basically VT, because in this case my VT and ER are same, and the air gap MMF. So what is the air gap MMF? Air gap MMF is basically air gap excitation MMF is here. So this whole angle is 90, right? This much I know. So this air gap excitation MMF, this angle is 90 and this angle is delta, right? So they're asking me what is angle between ER and FF. So it will be 90 plus delta. 90 plus delta, and ER lags the air gap MMF by 90 plus delta. So it will lag. So 90 plus delta will be the answer and it will lag. So option B will be correct. So actually this question is very good, and from this every doubt of your angles will be cleared. So in this one single question we have written the angle for everything possible. You can also derive the other angles, right? So I will just quickly summarize this question. Let me summarize this question. So we have been given a scenario where it is lagging load. So all this whatever we have discussed are for a lagging load. So the homework for you will be to solve for leading load, and tell me in the comments below what will happen for each of these questions. Please do this assignment, solve for leading load. Okay, I will quickly summarize this question again because I know there will be a bit of confusion here. Scenario was given to you that we have this power factor angle theta, that is a lagging power factor angle. Assuming leakage impedance is negligible. So leakage impedance is negligible, that means we don't have any drops. That means my resultant EMF, internal EMF, air gap EMF will be equals to the terminal voltage. I can neglect the leakage reactance, right? Only I have to consider the armature reactance. Okay, And the internal power factor angle is psi. Internal power factor angle basically means the angle between E and IA, that is basically psi. These two information were given to me. Okay, also like the this should also be given to you, that delta is the angle between the resultant EMF and the angle between the terminal voltage. Okay, these three information should be given to you. Now they are asking the angle by which the air gap excitation. If excitation is given, you will assume it to be field, right? Field flux, main field. So the angle difference between the air gap excitation MMF and the armature MMF, air gap excitation MMF, right? And the armature. So air gap excitation MMF is here, that will lead by 90 from the induced EMF, and the armature MMF is along the direction of the current, armature current I, right? So what is this angle basically they are asking? This angle will be this is 90, right? This angle is 90 plus this whole angle psi. So my main field MMF leads the armature MMF by 90 plus phi, which is present in the option A. Second question, the angle by which the resultant MMF. Now what is resultant MMF? Resultant MMF will lead the resultant induced EMF by 90 degrees, right? So what is the induced EMF? Vt. So resultant MMF will be here. So Fr will lead the induced EMF by 90 degrees. Okay. So now what I can say is basically what I can say is, now they are asking me the angle between this resultant MMF and the armature MMF. So resultant MMF is here 90 degrees and this much is theta, right? Armature MMF. So angle will be 90 plus theta and the resultant MMF will lead by 90 plus theta. Hence it leads by 90 plus theta. Okay. Now coming back to the third one, the angle by which the excitation EMF is basically whenever this excitation term is there, that means they are talking about the field EMF, right? This one, and the resultant MMF is here. So this whole angle is basically 90, right, from the Vt, and this angle is delta. So how much will be this angle? 90 minus delta, right? And my resultant, basically my field EMF will lag the resultant MMF by 90 minus delta. That's why it lags by 90 minus delta, because it is in the clockwise direction. The angle by which the air gap EMF dash the air gap excitation MMF. Okay, so air gap EMF is air gap EMF, right? So air gap EMF, if excitation is not present, that basically means they are talking about the resultant EMF, that is here. Okay, and the air gap excitation MMF is here. So they are asking me the angle between this and this. So what will be this angle? This angle will be simply this is 90, right, and this is delta. So 90 plus delta, lags by 90 plus delta. So basically this angle and this angle are the same, right? They're talking about same angle. This angle 90, sorry, no, these are not same, these are different. Okay, sorry, these are different. This is 90 plus delta. So everything is different here. So this angle is 90 plus delta, right? This is 90 plus delta. Okay, so I hope now you have understood the angles, right? Basic difference between the angles. Now let's solve the last question of today's lecture. A 1 MVA 4.6 kilovolt. So the S rated is 1 MVA and the voltage is terminal voltage is 4.6 kilovolts, has an armature resistance I is equals to 2 ohms and synchronous reactance XS is equals to 20 ohms. What is the value of the per phase EMF at full load operating at unity power factor? So very simple, very easy to understand. So unity power factor basically means my cos theta will be equals to 1, sin theta will be equals to 0. They are asking me what will be the per phase value. So I know magnitude of the per phase EMF, right? Very simple. It is, I will use one formula, Vt cos theta plus Ia Ra whole square plus Vt sin theta plus Ia XS whole square. Okay, so this will be equals to so what is Vt basically? So Vt is 4.6, sorry, this is star content, right? So Vt will be 4.6 divided by 3, under root 3, right? Sorry about that. And what will be the IA rated? IA rated will be basically this S1 MVA divided by root 3 into line voltage, that is 4.6 kilo, right? That will be 10 cube. This will give me the IA rated. So this will be 10 cube divided by 1000 divided by root 3 into 4.6, so 125 amperes. This will be the rated current. So from here I can simply solve it, right? So Vt is 4.6, right? So what is 4.4600 divided by root 3, so into cos theta, so this will be 266,2655.8 into cos theta. Cos theta is 1 only, plus I into Ra, so 125 into Ra, Ra is 2 whole square, plus Vt plus this will be Vt, that is 2 sin theta is 0, right? So this will be 0 only, it does not matter. Ia into xs, Ia is 125 into xs is 20 whole square. So from here I can easily find out. So this will be plus 250 whole square plus 125 into 20 whole square whole under root. So your induced EMF will be 3833. Okay, how is it lower? Oh, it is, okay, no, it is not lower, this is higher only. So 38.3324 will be your induced EMF value, or you can directly write down basically the, what do you call, you can directly write down the okay, let me see this, full load per phase, yeah, per phase generated EMF at full load, yeah. So you can directly write down per phase generated EMF as 3.833 kilovolt. This will be your answer for the question. Okay, so yeah, I hope you have enjoyed this lecture, because lot of misconceptions were cleared in this lecture. I have explained each and everything, like, and whatever doubts you might previously have, dropper students, I know you might have huge amounts of doubt. All those doubts are cleared in this lecture. Okay, this was just the first topic. We will clear each and every topic with basics, trust me on that. So I hope you have enjoyed. If you did, make sure to hit the like button. I will see you in the next lecture. Until then, happy learning.